Okay, today's the first. Good deal. Okay, let's take a look at this. Sine x over 1 minus...
Sorry.
Jake, how you doing? Good deal. The video for Thursday's class is going up on YouTube. It'll be up there pretty soon, Jake, within a day or two, so you can check it out and see exactly what I did on Thursday. Okay. All right, sine x over 1 minus sine squared. Well, it's certainly not an integration form that we have. We have sine x, we have cosine x, we have secant squared, we have things like that. What do you have to do? You're going to have to change this somehow. How do you change this? Well, what's 1 minus sine squared equal to? That's equal to cosine squared. That's another thing I will do sometime soon, is give you a piece of paper with trig things to know. One of these days I will do this, okay? Now, sine over cosine squared, you can't do that integral. We'll have to change this. And if you can look at this and see that what you have is this, okay, break it up. And what is sine x? Sine x over cosine x is tangent x. And 1 over cosine is secant. And the integral of secant tan is secant. And that's secant x. Okay. So there's a little trickery here to get it to the integration form that we need. This is something we're going to have to do in subsequent chapters, that kind of manipulation. I'm not sure it belongs here now, but I think they're giving you an indication that sometimes you're going to just have to change it to get something you can integrate.
You know, I did it. I made one mistake and I used cosecant and not secant, so I couldn't go anywhere with it. It didn't make any sense, but that took.
Okay. Okay. All right. Any other questions at all? Anything else? Yes.
Can you go over a problem? Was that a problem?
Yes, it was.
I have another one.
Go ahead. Hey, we'll do as many problems as you want.
It was 6 sine x minus 6 e to the x.
6 sine x minus
6 e to the x.
6 e to the x. Well, what they want you to realize is we can split this up. Here, let's do it a step at a time. We can split this up, first of all, on two integrals. Okay. Because that's a property we have. The integral of the sum or difference is the sum or difference of the integrals. Constants can be taken out front. And now, the integral of sine is a negative cosine. And the integral of e to the x is e to the x. Okay? And that's what they want you to do. I don't either. Well, how does your answer differ from this? It's how it differs.
I don't know, I just don't remember I kept on putting it in.
Oh, well, I gotta admit.
What was the answer I put?
Well, I don't know. The way you put it in, maybe? I don't know.
Or KC, I don't know.
Well, it shouldn't be that picky, but there are times. This is a good point, too. You know, you put something in WebAssign, and it'll say no, or it'll say incorrect or something. But it indeed may be correct. They want a different form. They want the decimal to 3, 4 decimal places, or they want it one way or another. You know, in those cases, there's a couple of possibilities. One possibility is to tell me or email me and say, Burns, I put this in, it is correct. Change my score. And I would just change your score. So I wouldn't, So I would do that with that particular one. That's what you had put in?
Yeah.
And it didn't like it?
Maybe I tried submitting it too many times, I don't know. Could have been something.
How many takes do you get in WebAssign? 5, I think, yeah. So if it was more than 5, yeah, maybe. But just send me an email and I'll change the score.
It grays out the input box when that happens.
Yeah, it does something. Yeah, so it doesn't allow you to put any more. Whatever the reason is, email me. I'll change it. We can do it. Any other questions at all? Yes?
So with what initial velocity must an object be thrown upward to reach the top of a national monument, which is 570 feet?
So we want to throw some object up.
What velocity?
With what velocity is, we'll call that x or something, so that its maximum height is equal to 570. That's what we want to do, right?
Implicit differentiation, that's the strategy to get the answer here.
Well, yeah, well, let's take a look. We know that position at any time t is equal to a negative 1/2 gt squared plus v sub naught t plus s sub naught. That gives you your position at any time t. The velocity is equal to gt, negative gt, plus v sub naught. Okay. Knowing that, we want to find this initial velocity, v sub naught, so that the maximum height is 570 feet. So let's see. What we want to do is find the velocity so that this maxes out at 570. When is this going to be a maximum? When the velocity is equal to 0. So if we set our velocity equal to 0, okay, and we don't know the time either, do we? No, we don't know much, do we? Okay, we do know it's feet per second. So we get negative 32t plus v sub naught is equal to 0. We're looking for the time and v sub naught. So given that, we want this s to be, well, the initial position is equal to 0. We're throwing it from the ground up. We want to find this, so this is equal to 570. So what do we know? We want to find the time it takes for the velocity to be 0, because that's what happens at maximum height. We also know that we're starting from the ground, and we want that height to be 570 at that time. So we have two equations and two unknowns. I think the best way to solve this would be, I could solve for v sub naught. Let me do that. Okay, is everybody with me on this? Okay. So solve for v sub naught. V sub naught is equal to 32t. So I have negative 16t squared plus 32t times t squared is equal to 570. Whoa. Wow. Okay. So I know that 16t squared is 570. What the heck? Why not make a monument 640 feet high? I mean, what would have been, all right, but anyhow, so what? Okay, so t squared is 570 over 16. The time is going to be the square root of 570 over 4. We got perfect squares in there? Hey, how you doing?
Good, thank you.
Last name?
Eddie Carey.
Oh, yeah, Rabin. Good. Nice. Okay. Nice. Square root of 570 over 4, whatever that is. Now, I'm going to take this time and solve for v sub naught. That initial velocity would be equal to 32 times the square root of 570. Okay. And let's see, 570 is what? 10 times 57. That's 10 times 3 times 19. So there's no perfect squares in there. So over 4. So I have 8 times the square root of 570. Now, it all depends on what WebAssign. See, here's another example of such a thing. What form does WebAssign want this? The decimal rounded, like 4 decimal places or something?
Decimal and 2.
2 decimal places? All right. I need someone to crank this out. Yes? 5.97. That can't be right. 5.97?
Yeah.
No.
It gives me that one. 570 squared.
That can't be right, Carlos.
190.99.
190.99. So I'm going to go with 191.
Well, this.
Hey, Egg. How you
If
doing?
they're having to go to 3 decimal points. then it'd be 190.997.
Okay. Hold on a second. Okay. So 190.997. So let's go with 191.00 then. I don't know what you did there,
You
Carlos.
have to multiply times 32, right?
No.
Yeah. Now-
Well, I did the 4 into 32 8 times, so it's 8 times the square root of 570.
Now it gives me 191.04.
That's still off a little bit for some reason. I'm not sure. Do you trust? I mean,
I know that one's more accurate.
what?
That one with the algebra system is super duper accurate.
Wait. This is not a complicated problem. So, if Jacob is telling me the square root of 570 times 8 is 1, go ahead, tell me again.
190.9973822.
That's what I got.
And Carlos, you're telling me it's something else? Something is wrong.
8 times the square root of 570
Yes.
gives me 109.997.
All right, there we go. We're all in agreement and everybody is happy. This is good. Okay. So rounded to 2 decimal places, 191 feet per second. I don't know if I'm still on the thing. Yes, I am. Okay, there you go. So you'd have to launch this thing at 191.00 feet per second. Okay? Now this is, yes,
Is
Eddie.
this number 25 on the home?
Yes.
I don't know.
Yes.
You may have different numbers though. You may have different numbers, Abby.
Looking for what the max height was.
We could have different.
Yeah, everybody could have a different number. Okay.
Yeah, like mine was 550.
Yeah, that's what WebAssign does. You know, it's interesting we did this because a few weeks ago we were at my son's, whose daughter was having a birthday, my granddaughter's birthday. And one of my son-in-laws brought one of those potato launcher things, those tubes, and you spray hairspray in it. And then he did something like lighting the hairspray and shot this. What was he shooting? He was shooting
Potatoes?
Well, he wasn't shooting potatoes. He was shooting apples because he had apples. And they were, wham, they would go far. And the question was, how far did they go? So what we did, we timed it, figured out the angle, 45 degrees, and with those 2 pieces of information, we figured out the distance. It was cool. So I was a big hit at that party. The only time. What's that?
What was the distance?
I forget, but it was real far. I mean, like 480 feet, or maybe even more than that. It was far. That thing was really powerful. It's a tube. What do you call those white plastic?
PVC.
Yeah, that tube. Yeah, and you put hairspray in it. You know this procedure?
Yeah, you can use hairspray, or there's like liquid rocket fuel that you get for hobbyist use.
Liquid rocket fuel.
So you're supposed to be able to put it in like a toy rocket that you launch off, but you can also launch a potato with it.
Well, when it comes out, does it come out as French fries or what? I imagine. Wow.
Well, you just gotta put the little dicer on top, and then.
Yeah, there you go. Okay, anyhow, that's what you get. Okay. Yeah, how are we doing? Is this okay? Good deal. Any other questions on homework? Okay, let's move on. Here's the deal. In Calculus 1, the problem was to find the slope of a tangent line to a curve at a given point. That was the problem to solve. And we solved that by taking the point on the curve and taking another point, a distance delta x away, finding the slope of the secant line through those 2 points, and then letting the delta x go to 0. We took a limit and let delta x go to 0. That limit of delta y over delta x as delta x goes to 0, that's the derivative. That's a Calc 1 problem. That's the problem you solve in Calculus 1. So when Isaac Newton solved, okay? And looking at planetary motion, okay? In Calc 2, we have a different problem. The problem is, given a curve, okay, function, we want to find the area under that curve. That's the problem we want to solve. Okay? It turns out the solution to that problem is the inverse to finding the slope of the tangent line. Slope of the tangent line is a derivative. The area under the curve we're going to show, I'm going to do a little proof next class, that is the antiderivative. Okay, it's kind of interesting. But what we're going to do now, today, is we're going to take a function and we're going to get an approximation for the area by dividing it up into little pieces, okay, rectangles, and then we're going to sum up all those rectangles to get an approximation, and then we're going to let the number of rectangles go to infinity, so that the delta x's, okay, the width of each of these little subintervals, goes to 0. It's another limit problem. The solution to that will be the antiderivative. The solution to that is the area under the curve. Okay? So, but in order to do this, the first thing we have to do is do some sigma notation, some summation notation. Sigma. Okay? Greek letter sigma in mathematics always represents a sum. Okay? For example, if you have something like this, this says to find the sum of the first 5 integers. Start I at 1, increment by 1 each time to get to 5. This would be 1 plus 2 plus 3 plus 4 plus 5. Okay? That's what that notation means. Okay? That sum would be 15. Okay? You're going to be given a bunch of problems, okay? You're going to be given, and I'm going to give you a couple formulas to use on this. There's a pretty famous problem, this problem here. One plus 2 plus 3 plus 4 plus 99 plus 100. The story goes like this, and supposedly this really happens, is Carl Friedrich Gauss was like 2nd grade. Wait a second. What grade is she in? 4th. Wow. All right. So, well, let's say Carl was in 4th grade, all right? And the class was being unruly. And the teacher said to the class, all right, to keep you guys quiet, I want you to add up the numbers from 1 to 100. Okay? Well, immediately, little Carl Frederick raised his hand and said, okay, the answer is 5,050. And then the teacher said, looked at the answer, agreed, and then walked over with a stick and whacked him on that somewhere in the hand. I don't know, whatever they did those days, you know what I mean? And she gave him a whack. And supposedly what he did was this. He said, well, the sum we're looking for here, let's call this S. And if I rewrite it backwards, that's also S. And if I add this up, I'll have 101. I have 2S. And how many 101s do I have here?
100?
100, thank you. I have 100 101s. That's 2S. Divide by 2. 2 goes into 150 times. 50 times 101 is 50/50. Okay? So, and supposedly he just did it in his head. Okay? Because little Gauss was like awesome. Okay? And that's the way he did it. But there's a formula for this. This is the formula you should know. Okay? The sum of the first n integers. This is one thing I would expect you to know, actually, because we're going to use it occasionally, today in particular. The sum of the first n integers. This is an arithmetic series. This is something you should get in pre-calculus along the way somewhere, like in a tech math or something. Does anybody know the formula for the sum of the first n integers? Yes. Oh, wait.
N times n plus 1 times d.
Oh, no. Boy, I thought you had it there, too, because you were really close. I mean, almost. What were you going to say?
I was going to say, so it's n plus 1, right?
Well, n plus 1 is in there, yeah.
Okay, so I would say
You can get it from what Gauss did here.
n is how many numbers there are, so it'd be
Yeah.
n plus n. Wait, no, I can't figure out a way to word it.
Oh,
I can't figure out a way
okay.
to word it.
okay. All right, but look, all right, just give me, let me give you just another couple seconds. Look at what Gauss did here for the sum of the first 100 and see if you can generalize that. I mean, it's not a big deal. I just see if you can do that. You were, he was on the right track. He kind of was on the right track. You're on the right track. There's a formulas you get in pre and tech math or pre-calc involving the common difference, the D stuff. But Jake,
Is it n times n plus I over 2?
it's n, whoops, times n plus 1 over 2, because we're starting with 1.
Well,
Okay.
but wouldn't I be the generalization if we change I?
Well, then you got two variables in there, and we want it in terms of n. I want the sum of the first n integers, and it's n times n plus 1 all over 2. And check out what Gauss did here. What did he do? When he added them up, he got n plus 1. Okay? This is n plus 1. And there's n of those, n plus 1s, but you had to divide by 2 since we sum them up to get 2 times the sum. That's the formula for the sum of the first n integers. Jacob?
Will it still work if I is 2?
No. This will add from 1. If you wanna find the sum from, let's say something else, 10 to, well, here, let's go 10 to 100. Okay, what do you do here? You find the sum from 1 to 100 minus the sum
Okay.
from 1 to 9. Okay, and that'll give you that. So you use the formula on this, use the formula on that, and take the difference. Okay, and that works. Okay, that's the kind of thing you have to do. This is one thing you should know. You should know that sum is n plus 1 over 2. There's another one that we're going to use, and that's I equals 1 to n I squared. This is 1 squared plus 2 squared plus 3 squared plus n squared. Okay? I'm not expecting anybody to know this one. It's n plus 1, 2n plus 1, all over 6. Okay? How do you prove such formulas? You know how to do a proof? If you take discrete structures class, in that class, as a computer science major, you probably should take discrete structures. Okay, after Calc 1, Calc 2, you generally would take Calc 3. Computer science don't even have to take Calc 3. But then they would take diffie Qs, double E's would take diffie Qs, but computer science people should take discrete structures. And in that class, you learn how to do these proofs, okay? This would be a proof by induction, it's called, okay? And you do the proof. But it's kind of interesting. It's interesting stuff. Math majors, for sure. Wait, have I asked you this already? Math majors? Do we have math majors in here? Any math majors? Any A students in here, in other words? No. Just kidding. No math majors, really? Oh, fine. Fine. Whatever.
Can we simplify
Huh. Can you simplify that? How? What do you want to do? Be careful here, Jacob.
Never mind.
Okay, good. All right, because that's as simple as you can make it, okay? All right, that's the sum of the first n squared. You know what's interesting? We don't need this one, but this one, it's so interesting that this would be the case. I'm just going to throw this out here. If you do the sum of the first cubes, like I said, we don't need this. It's equal to n plus 1 over 2 squared. It's really kind of cool. Okay, it's the square of the sum of the first n integers, which is really surprising, it seems to me.
Well, it's like that when you graph them, you have the original equation, and you have which is the line, and then you grab the.
And then you
If
get.
you do it to the fifth, they'd have the same pattern.
Well, there you go. Well, that's a possibility. It's just kind of cool. All right, so we're going to need these couple and to do what we're going to do. Also in this section, this is chapter 5.1, 5.2. they're going to give you problems like this. They're going to ask you to do these kinds of things. Actually, there's one more you should know here. Let me give you this one here. There's one more you should know. This is one you get. This starts at 0, this one here. This is an infinite series, okay? This seems to me you should get in tech math. This is a geometric series. And it's interesting because at the end of the course, we're going to come back to infinite. Geez, that's a 4 there. Okay. The last chapter, we do 5 chapters. There's chapter 6, we only do 1 section. The last chapter we do, the whole chapter is on infinite series, sequences and series. It's kind of interesting. And we're going to bring this up again. So we're going to see this again. This is a geometric series. That's something you should get in tech math as well. Anybody know the sum of an infinite geometric series? Do you know that? That sum is A over 1 minus R. A is the first term. R is called the common ratio. Okay, and this is true as long as the absolute value of R is less than 1. Okay, what's that? Well, it depends on what the series is. Is what one? The sum? Depends. I can give you one whose sum is 1. You ready for this? Here, watch this one. This is Zeno's paradox. Okay. Zeno's paradox goes like this. You know Zeno's paradox? No? Okay. Zeno's paradox goes like this. Let's say we take a student and we stand the student up right there. Okay. And let's suppose, well, Zeno was like 400 BC, so he didn't have a gun or something. So shoot an arrow at the student, okay? And what has to happen is the arrow has to go halfway, okay, to get to the student. And then it has to go half the remaining distance. And then it has to go half the remaining distance.
So theoretically, it never reached the wall.
Yeah, that's right. And then go half the remaining distance, and half the remaining distance, half the remaining distance, half the remaining distance. There's always a half a remaining distance to go. The arrow never reaches the student. We could test it out and see what happens there. We wouldn't want to do that, though. But obviously, that's false. We know the arrow does reach the student. The reason Zeno couldn't comprehend that is because we end up with an infinite series with a finite sum, okay? And they had no means, no mechanism to deal with such things. His conclusion was, you know what his conclusion was? There's no such thing as motion. That was his conclusion. He concluded that. He couldn't get out of this conundrum, this paradox, and that was his conclusion. But if you take the sum of 1/2 the distance because of 1/4 and 1/8 and 1/16 and 1/32, etc., that's an infinite geometric series. Each term is multiplied by 1/2 to get to the next term. R here is equal to 1/2. A is equal to 1/2, first term. R is equal to 1/2. As long as R has an absolute value less than 1, the sum is equal to A over 1 minus R. So in this particular case, we have 1/2 over 1 minus 1/2. We have 1. The sum is equal to 1. The sum of that series is equal to 1. Yes, the arrow does get to the student. Okay? The sum of that infinite series is indeed equal to 1. There's a lot of variations on them. They're kind of cool. Something, you know, the hare and the tortoise kind of thing. They're going to have a race. You give the tortoise a head start of like 100 yards or whatever. And the hare can go 10 times as fast. But as soon as he catches up to where the tortoise was, the tortoise moves ahead a little bit. And then as soon as the hare catches up to where the tortoise is now, the hare moves ahead a little bit more. As soon as he catches up there, the hare, the tortoise moves a little bit more. He never catches them because that tortoise always goes that little additional distance. But when you sum up that infinite series, it's kind of cool. Here's that infinite series. Let's say it turns out to be 10 plus 1 plus 0.1 plus 0.01. And each time the time increment is going smaller and smaller and smaller, obviously, because the distance traveled is smaller and smaller and smaller. Can we tell me what the sum of that is? Well, maybe it is geometric. You could use the formula for geometric series, but you could also use your brains and say, well, that's 11.1111 repeating, and what's 11.111 repeating equal to? What? Well, it's a little over 11, but 11 and the decimal 0.11 repeating is equal to?
Get that plus 0.1.
No. This is a little bit greater than 11.1. I'm asking you the decimal, yes.
100 over 9.
It's 100 over 9. Is that what you said? Yes, it's 11 and 1/9. That's it. It's 11 and 1/9. 0.111 repeating is 1/9. 222 repeating is 2/9. 333 repeating is 1/3. 3/9. Okay. 444 repeating is 4/9. 555 repeating 5/9. 666 repeating 6/9. 2/3. 777 repeating is 7/9. 888 repeating is 8/9. What's 999 repeating? 1. It's 9/9. Okay. It's equal to 1. Okay. It's equal to 1. 0.999 repeating is equal to. Oh, okay. Wow. All right. I'm just wandering around. Okay. Oh, well, what about this one? What about this one? I just said when we repeat the single digit, okay, 111, 19, 222, 2/9, etc. Okay. What about when you repeat two digits? 17, 17, 17, 17, 17. What's that equal to?
17 over 99.
You bet it is, Dan. No way, that Dan guy is good, man. If you repeat two digits from the decimal, it's going to be those two digits over 99. Why is that? Well, because if you let n equal this, and then multiply by 100, that moves the decimal point over, so they line up again, and then do a subtraction, and then divide by 99, you get 17 over 99. Okay? So what's 0.126, 126, 126, 126 repeating equal to?
126 over 999.
Perfect. Yes, it is. Yes, it is. Okay, last one in this, and then, well, no, because there's some other little things here, but let me just give you this one. What is this one equal to? Okay. Just think about it. Wow, Abby, yeah, that's it. Good. Good job. Yes, 1 over 45, because what happens is it's the 2/9 times 1/10. That's 2/90ths, which is 1 over 45. Okay? Everybody else set on that? All those numbers, all those repeating decimals are rational numbers. They can be written as a fraction, okay? If a decimal is infinite, non-repeating, then it's irrational. Okay? Irrational. And when we do infinite series in the last chapter, we'll talk about that a little bit more. Okay, one other thing I do want to mention about these series that they're going to give you. They're going to give you series like this, and they're going to ask you to come up with a formula for the nth term. So, for example, if you had something like this, let's say you have -2 plus 4 plus -8 plus 16 plus -32 plus etc. And they want you to write it in sigma notation. Okay. How would you do that? What would that be?
It's going to be n to the n plus I.
No.
It's not that your exponent is you're taking 2 and then like -2 and then you're squaring it and then cubing it. And then
Okay, so what did you write again?
That is, I'm sorry, x to the n plus I.
Okay, first of all, your formula here has to be in terms of I only. The only variable in your formula here is going to be an I. Okay? I is going to go from 1 up to n. Actually, if this is infinite, it's the limit then as n goes to infinity. Okay? Okay, so I need a formula here in terms of I only. So if you can give me that in terms of I only, that would be exactly what I'm looking for. Okay, go ahead.
-2 raised to the I.
That's perfect. Works out just right. Wow, that's really cool. Okay, that's not what I was thinking of, but that works better than what I was thinking of. So that's pretty good. Not away. Okay, when I is 1, you get -2, plus when it's 2, you get 4. I was thinking about doing the -1 to the I to get the plus minus, and then get the 2 to the I to get the 2 power of 2's. But you put them together in one and a better approach. Good job. Okay. All right, how are we doing? Okay. All right, here's what we really want to do. Okay, what we really want to do is the following. We really want to take a function. Let's take x squared. And let's take an interval from 0 to 1. We want to find the area under this curve. Okay? We want to find the area under this curve. What we're going to do is the following. We're going to divide this interval up into pieces. The width of each subinterval will be a delta x, and we're going to make rectangles over each of these subintervals. Okay? We're going to sum up the areas of these rectangles. Let's take a look. Let's start with 2 rectangles. Okay? Let's take the midpoint. Now we have a choice. We can take left endpoints. In other words, if we take left endpoints, we'll start here, and this will be our first rectangle, and this will be our second rectangle. This is using left endpoints. Okay? So let's do that. The area in terms of these 2 rectangles using left endpoints, okay? The area, these 2 would be, well, let's see, this is 1/2 0. Area of the first rectangle is length times width. The width is 1/2. The length we'll call the height here. The height of the first one, since we're using a left endpoint, is 0. Okay, it's going to be f of 0, which is 0. Plus, the second rectangle, this guy, the width is 1/2. Its height is f of 1/2. Okay. The area of these 2 rectangles is going to be 1/2. F of 0 would be 0, plus 1/2. F of 1/2 is 1/4. We end up with, and I'm going to factor out a 1/2, 0 plus 1/4. And that's equal to 1/8. Now, how good an approximation is that? It's not good. I mean, is it greater than the actual area, equal to the actual area, or less than the actual area? It's less than the actual area, okay? So, Abby, at the end of this, by the end, I'm going to be an expert in reading your lips. Is that what I'm going to be doing? All right, which is okay. All right? Okay, it's going to be less than the actual area. All right? Let's take the right endpoints. Okay, the area of here, I should put 2L here. I'm going to put 2R here. Okay? All right, well, let's see. The right is going to be this one plus this one. Okay? Those are the right endpoints. So, what's it equal to? 1/2 times this height, f of 1/2, plus another 1/2 times f of 1. That's this height right here. That's equal to 1/2 times 1/4 plus 1/2 times 1, f of 1 is 1. We end up, I'm going to factor out a half. You get 1/4 plus 1. Okay? And that's equal to, let's see, that's 5/4 here, 4/4 plus 1/4, 5/4, 5/8. How's that look? Now, is that area too big, just right, too small? Too big. The actual area is somewhere in between. Actually, we could get a pretty decent approximation by taking the average of these two, in effect making a trapezoid out of this. And there's something called a trapezoidal rule, which is fairly accurate when it comes to approximation of areas under curves. Okay, numeric integration is what it's called. Okay, so how are we doing so far? Everybody okay with this? We want to do better. What I want to do is get a better approximation. I want to go to, we have to do this once in the semester, okay? It's torture, I know, but we have to do this once. We have to do this out the long way. It's like finding derivatives by using the limit definition. You know what we had to do? And then we had some properties where we could just forget it. We didn't need the limit definition because we could use that limit definition to prove some properties and then develop some derivative forms, okay? Does that make sense? We need to do this once so that we can develop some rule, and then we can use the rule all the time. But we have to do this once. You guys don't look too pleased here. I mean, Jacob's smiling, but I don't know. Nobody else is smiling here at all. She's smiling. All right, Jacob and her. All right, I'm going to teach to her. I'm going to teach to Jacob. That's it. All right. Good deal. Keep smiling. Good deal.
I can't hear anything you're saying.
Oh, good. That's all right. That's probably why she's smiling. She can't hear a thing. That's okay. All right. Let's go to 4. Here, I'm going to do a new page. We'll go to 4 rectangles. And I hate to tell you this, but on your homework, you're going to end up having to do one of these anyways. Okay. Here we go. Y equals x squared, same thing. Okay. Now I'm going to divide it into 4 parts. Okay. Okay. And we're going to do the area of 4, and we're going to take left endpoints. Can you read that when I write it that small? Can you read that, Carlos? No, huh? Oh, boy. Okay. How about that? Okay. We're going to do the area in terms of 4 left endpoint rectangles, and that area is equal to. Now, when we do the left endpoints, we're going to. Here's the first rectangle. Use the left endpoint. That's this guy. Here's the second one. Here's the third one. Okay. And here's the fourth one. Okay. So let's do it. Here we go. First one is 1/4 times the height of f of 0 plus. Next one, the second one is 1/4, okay, times f of 1/4. That's this right here. Next one is 1/4 f of 1/2. That's this height right here. That's this rectangle right here. Plus 1/4 f of 3/4. Okay? In terms of 4 left endpoint rectangles, that area, which is an approximation for the total area, is 1/4. Now, f of 0 is 0. F of 1/4, 1/4 squared is 1/16. 1/2 squared, 1/4. 3/4 is 9/16. Okay? That's equal to 1/4. I'll tell you what, I'm going to put it all over 16. Okay? And I'm going to have 0 plus 1 plus 4 plus 9. Okay? And that's equal to, let's see, 10, 14 sixteenths, okay? That's 14 over 64. That's 7/32, I believe. Check it out. Make sure it's okay.
14 over 3/4?
What is it?
No, yeah. Wait, what did you say was over?
It's 14 over 64, 7 over 32. Wait.
Did you, what? Oh, never mind.
Okay, you okay?
Yeah.
You sure?
I understand what you're saying.
Okay, that's okay. That happens a lot. People tell me that all the time. Okay, that's left endpoints. Let's go to right endpoints, okay? That area is 1/4. Now, the right endpoints, here's the first one here. Here's the second one here. Here's the third one here. And here's the fourth one here. Ooh, boy. Okay, like so. All right, so what's my first height when I take right endpoints? F of 1/4, thank you. Just want to make sure you guys are with me. Next one. Thank you very much. Next one. That way. And the next one? F of 1. Very nice. Okay, so that's going to equal F of 1/4, 1/16, 1/4, 9/16, 1. I'm going to write 1 in the form of 16/16, so maintain this pattern. And that's equal to 1/4. Put it all over 16, so I get 1 plus 4 plus 9 plus 16. And that's equal to, let's see, that's 30/16, that's 30/64, that's 15 30-seconds. Okay? So the actual area under this curve, under this graph, is somewhere between those two. Probably somewhere really close to the middle of these two. Somewhere like 11 30-seconds, really close to being 11 30-seconds. But this is a better approximation than what I had before. Okay? What's that?
It's still an approximation.
It's still only approximation. Yeah, I've got equal signs because that's the area of the 4 left and that's the area of the 4 right, but these are approximations for the area under the curve. How could I get a better approximation?
Using limits?
Yeah, good answer. Okay, good answer. What we could do is take 8 and 16. We could keep doubling the number of rectangles, or we could generalize this result and then take a limit. That's exactly what we are going to do. So here's what we're going to do. We're going to divide this up into n rectangles. Okay? Here we go. We're going to take this and divide this up into n rectangles. Okay? Like so. We're going to find the area in terms of n left endpoint rectangles, and then we're going to find the area in terms of n right endpoint rectangles. And then what we're going to do is take the limit as n goes to infinity for each of those sums. What should happen when we take the limit as n goes to infinity of each of those sums? Yes, thank you. That's exactly right. We should come up with the same number. And that same number will be the exact area under that curve. So one of them, the left end points, are approaching that number from underneath this way. The other one is approaching from above this way. And what's going to happen is the limit, if it's the same limit, will be right in between. And that limit will be the exact area of that curve. Okay? What's that? Okay, so let's do it, okay? Let's do it. Now this process here of doing this sum, my Calc 3 class, okay? This morning we were doing areas of polar graphs, and it's the same process. You do this to develop this little formula, and then you let n go to infinity, and what you end up with is a Riemann sum. That's what we're aiming for, and that's evaluated with an integral, and that's what we're aiming for, okay? All right, so let's do it. All right, the area in terms of left endpoints, okay, is equal to Okay, now, what are the coordinates of this first point? If I'm going to divide this up into n equal subintervals, what are the coordinates of this point right here?
That one?
Yeah, that one right there. The first one.
And,
What is it?
and
No.
it'd be the limit of x.
No, it's not a limit. If I'm going to divide this up into n equal subintervals, what is it?
N plus 1.
No.
Is it 110 over n?
No.
That is 110 over n.
What's 110? Where's 110? Oh, that's 1 comma 0.
Oh.
But there's infinitely many points
It
in
would be
between.
1 over n.
Yes, it would. 1 over n, he said it. Okay. Okay, this is 1 over n. If I divide an interval of 1 unit length into n equal parts, each part will have a width of 1 over n. Okay? The first point here will be 1 over n. What will the next point be? It's x coordinate anyways.
Plus 1. 1 over n plus 1.
What is it? 2 over n. Okay? It's 1 over n plus another 1 over n, 2 over n. You said plus 1. You kind of had it. What's this guy?
3 over n.
3 over n. Each little width here is 1 over n, okay? 4 over n. What would this point be?
N minus 1 over n.
Wow, nice job there, man. N minus 1 over n, or 1 minus 1 over n. I like his way better. And the last one is 1, which we could write to maintain the pattern as what?
N over n.
N over n. Very nice. Nicely done. Okay, I'm going to take left rectangles first. So that's this guy, that's this guy, that's this guy, that's this guy, and then finally this guy here. Okay. Whew. All right. So, in terms of left endpoints, that area is equal to. Now, the width of each one of these is 1 over n. So it's 1 over n times. What's the first height of the first left endpoint rectangle? F of 0. Is that you, Carolina? Was that you that said that? Oh. Okay. All right. I just want to. Okay, F of 0. Plus, what's the second one? The width is 1 over n. Each width is 1 over n. What's the height of the second one? That's this height right here.
2 n?
F of 1 over n. Okay. How are we doing? Brenda, you okay? You hanging in there?
Yep.
Okay. All right. All right. All right, next one. 1 over n times f of 2 over n. Thank you. And one more. 1 over n, f of 3 over n. Okay, and what's this last one here? 1 over n times f of
N minus 1 over n.
n minus 1 over n. Good deal. Okay. I'll tell you what I'm going to do. I'm going to do the left endpoint ones. I'm going to do them all out, and then I'll do the right ones. Okay, so here we go. So in terms of left endpoints, that area is, in the left endpoints, I'm going to factor out a 1 over n. I have f of 0. Okay? F of 0 would be 0. Plus, f of 1 over n is 1 over n squared. Plus, 2 over n is 2 squared over n squared. 3 over n is 3 squared over n squared. Okay? Plus n minus 1 squared over n squared. Okay? How are we doing? Nice. That's equal to 1 over n times. I'm going to put everything over n squared. And I'm going to have 0 squared plus 1 squared plus 2 squared plus 3 squared plus n minus 1 squared. Okay. Now, I gave you a formula for the sum of the first n squares. Okay? The formula for the sum of the first n squares is n plus 1, 2n plus 1, all over 6. I'm going to use that formula right now on 1 squared plus the 0 squared is 0. Who cares? This is the sum of the first n minus 1 squares. All right, here's the formula. The sum from I equals 1 to n, the sum of the first n squares is n plus 1, 2n plus 1, all over 6. That's the formula. Okay? So, what do we get? We have 1 over n. I'm going to apply the formula to this sum of the first n minus 1 squares. So I'm going to use this formula, but instead of n, I'm going to have an n minus 1, because I'm only taking the sum of the first n minus 1 squares. Okay? So it's going to be n minus 1, n minus 1 plus 1, 2 times, write it out, 2 times n minus 1 plus 1.
Is that raised to the power or times?
Say that again.
Is that's 1 over n times this next
Yes.
statement? Okay.
Yes. Here's the 1 over n from here. Here's the sum of these here, and then it's all over n squared. So I got an n squared as well. Okay? Okay? How's that look? Ask any questions right here. This is a tricky
How are we
question.
finding n?
Well, n is going to go to infinity. In a minute, I'm going to take the limit as n goes to infinity. Okay, but I want to simplify this a little bit first. That's equal to, the n times n squared is n cubed, so down below I've got a 6n cubed. Up above I have an n minus 1, I have an n, I have a 2n minus 2 plus 1, which is a 2n minus 1. Okay? And I'll tell you what, I'm going to multiply this out as well. I'm going to do it. I'm going to multiply that out, n squared minus n, 2n minus 1, 6n cubed. Okay? And that's equal to, when I multiply it out, 2n cubed, okay, minus n squared minus 2n squared, plus n, all over 6n cubed. And then I could factor out n's. Boy, oh boy. So I get 2n squared minus 3n plus 1 over 6n squared. That's the area under that curve in terms of its left endpoint rectangles and in terms of n left endpoint rectangles. I want the exact area under the curve. To get the exact area under the curve, I'm going to take the limit, A, not A sub L, but A, the area under the curve, is going to be the limit as n goes to infinity of that sum. And what is that limit as n goes to infinity of 2n squared minus 3n plus 1 over 6n squared? Yes.
1/3.
You bet it is. I don't wait, Brennan. That's good. Well, what happens is you run across this limit. You do. Did we do that in Calc 1? That limit? Yeah, I think we did. If you think about dividing numerator and denominator by n squared, okay? Seems to me I've recently mentioned this too. Did I recently mention this? No, maybe not. No, all right, but anyhow. Here's the rule. Same degree, numerator and denominator. The limit as n goes to infinity is the ratio of their leading coefficients, 2/6. But if you divide numerator and denominator by n squared, if you divide the numerator by n squared, you get 2 minus 3 over n plus 1 over n squared. Divide the denominator by n squared, you get 6. Now as n goes to infinity, what happens to 3 over n? It goes to 0, thank you. And 1 over n squared goes where? 0. You end up with 2/6, 1/3. Okay? We get 1/3 for the area under that curve. Okay? In terms of its left endpoint rectangles by letting the number of such things go to infinity. What we're going to do now, believe it or not, is do the right endpoint rectangles and let n go to infinity there as well. Check this out. You guys still alive? Barely? How's she doing? You doing? She's doing okay? You doing okay? She can't hear me. Okay.
I can hear you.
Oh, you can hear me. Okay. All right. You doing okay?
Yeah.
Oh, barely. Oh, boy. I've only got about 3 more hours, okay? 3 more hours to go. Okay, let's do the right endpoints. Here we go. We only have to do this once a semester, okay? So that's
You
it.
have to do it in Calc 3 too?
No, because we'll have the process. We won't do this in Calc 3. We'll use the results in Calc 3, but we won't actually do this out, okay? Okay, here we go. F of x equals x squared. Okay. Again, I'm going to divide this up into n equal parts. And I got to tell you, it doesn't even have to be equal parts. As long as the biggest of these parts goes to 0 as n goes to infinity is sufficient. But we're going to use equal parts to keep it simple. This would be 1 over n still. That's still 2 over n. This is still 3 over n. That's still 4 over n. This is still n minus 1 over n. And this is still n over n. You okay with that one? Okay. Okay, the area in terms of right endpoints is equal to, now the right endpoint sum. Now I'm taking this rectangle, this rectangle, this rectangle, this rectangle, and finally this rectangle. Is equal to 1 over n. Now, the first height is going to be, what's the first height of the first right endpoint rectangle? F of 1 over n, thank you. Okay, we're going to start with that one, and then get 1 over n, f of 2 over n, 1 over n, f of 3 over n, etc., 1 over n. And what's the last one equal to? What is it? No. F of 1 or n over n. The difference between the two is this. The first one we started with the 0, and we end up with the n minus 1. This one shifted over 1 unit. We start with the 1 and end with the n. Okay? That's the difference in the two. Okay? So that's equal to 1 over n. That's 1 over n squared is 1 squared over n squared. 2 squared over n squared, 3 squared over n squared, n squared over n squared. Okay? That's equal to 1 over n. One squared plus 2 squared plus 3 squared plus n squared. But what is 1 squared plus 2 squared plus 3 squared plus n squared? That's equal to, what's the sum equal to? Sum of the first n squares? n plus 1, 2n plus 1, all over 6.
Why are all those
Go ahead.
squared there?
Why is what?
The second line, all the denominators are squared. Why is that?
Because each point, like the 4 over n, you have to, it's this height we're looking for, and this height is the value of the function at 4 over n, and the value of the function says to take whatever x is and square it. So this height right here is 4 over n squared.
Oh, because we use the function. Okay.
Yes, yeah. Okay? So that's equal to, all right, I'm going to multiply it out again. So I get 6n cubed down here. Up here, I'm going to have an n squared plus n. And I'm going to multiply by 2n plus 1. I'm going to have a 2n cubed plus n squared plus n squared. Okay, 2n cubed, n squared plus 2n squared, a 3n squared, and then an n, I think. I guess. All right, I think. Okay? And then I can take out an n, to get 2n squared plus 3n plus 1 over 6n squared. That's the area of the right endpoint rectangles. Now, we did a problem where n was equal to what, 4? Remember we did weight a long time ago? We had 4 right endpoint rectangles. If you put a 4 in for n here, we should get the answer we had from before of 15 seconds. Okay? And in other words, this works for any n. Put a 4 in here. See what you get. Just to verify this, if you let n equal 4, what do you get? You get 2 times 16 plus 12 plus 1 over 4 squared. Boy, this better come out. If this doesn't come out, oh man, we're going to be here for weeks. All right. 4 squared, 16, 96. That's 32. 44, 45 over 96. Okay.
15, 30 seconds.
Is it? Yeah, divide by 3. 15, 30. Thank you, Jacob. 15, 30 seconds. All I'm doing is verifying it works for n equals 4.
If you take the limit, it's the same.
If you take what?
Take the limit.
Let's take the limit. That's what we want to do.
1/3.
Okay. You took all the suspense out, Jacob. That's okay. That's all right. I'm sure there was no real suspense there. But anyhow, so the area is equal to, this is A, the area under the curve. The exact area under this curve is the limit as n goes to infinity of this sum of n rectangles. And it's equal to
1/3.
2, 6, 1/3 again. The same thing we got from before. One approached it from below, the other one, this one approached it from above, and they both have the same limit of 1/3. That is the exact area under this curve.
So
Okay.
many parabolas that applies to them, right?
What? This process?
The function is x squared.
Yeah, for this function over that interval, the area is 1/3. Now, if we want to do another function over another interval, we try it again for that, okay? But guess what? This one was really easy compared to some other ones. We had a formula for the sum of the first n squares. What happens if we have a 5th power? We don't have that formula. There is such a formula. What happens if we take the square root of something, or a sine function, or a log function, or an exponential function? We don't have formulas for such things. We need a better way. And that better, yes?
Would it be easier if you had the whole equation from -1 to 1? Like not only for x to the second, but for anything that intersects at 0, 0? Would it be easier to do the full equation or do half of it and add them together?
We're going to use the symmetry of the situation often. And sometimes, especially in that case, if the option is to go from, say, and sometimes you don't have symmetry even to use. If we have to go do that, let's suppose we do have the symmetry. We'll go from 0 to something and double it. It's often easier there than to go from -3 to 3, say. That's a good point. We're going to be aware of that when we do some of the problems. Okay. Here's the process that we're going to use to replace this. Now, I'm not going to do a proof of this today. I'm going to leave that for next time. But I just want to show you that this process can be replaced by doing the following. This area under that curve is going to equal an integral. Okay? We are going from 0 to 1. Those are called the limits of integration. This is called a definite integral. And the function is x squared.
So this is how we can actually find it
Yes.
past the
Yes.
okay, the tedious bit.
Yes.
Okay.
And I'm going to prove that this integral or antiderivative does indeed give us the area. I'll do that next time. Because I don't want to give you too much the theoretical kind of stuff like that, okay? Plus she's getting tired too, so no. But anyhow, but I'll do it next time. So the integral from 0 to 1 of x squared, what's the antiderivative or integral of x squared? What's the rule? We have a rule for that. It's x cubed over 3. And what we're going to do is substitute in the 1 and substitute in the 0. and get an answer. This right here, that replaces this. Okay? It replaces this. It's amazing. That integral replaces that whole process, that infinite sum. But this was an easy infinite sum. Okay? There are some, like I said, if we got trig functions and exponential functions and things like that, we don't have the formulas to use. This is an easy one, and that process replaced it. Brendan.
Where did the 0 come in that?
We started at 0. That was our left endpoint, and we went to 1.
Yeah, but up in the, like, where did you put the 0 in the whole integral part?
It's 1/3 minus 0.
Yes. I put the 1 in here, and then I put the 0 in. And I took the difference.
So we have to find the difference of by putting the value of 1 first and then 0?
Yes, correct.
Okay.
That's it. That's what we're going to do. Yes.
And you might have already answered this in last week's class.
Say that again now.
You might have answered this in last week's class.
Possible.
But,
If I did, I'm not going to answer it again. Jake. Go ahead.
Can you have, is there like a implicit underrative?
There's implicit differentiation. Is there an implicit integration?
Yes.
No.
So like I can't find the area under x squared plus y squared equals 1.
X squared plus y squared equals 1. The area, okay, what do you say? If you had a function, for that to be a function, you have to let z equals x plus y squared. That's a three-dimensional object, that's a surface. You could find the volume underneath that surface. That defines a surface in space. And in Calc 3, that's what you do. You take a surface, z equals some function of x and y, some surface here. And you find the volume underneath that surface over a region in the xy plane. That's what we'll do. And then you find volumes bounded by two surfaces. And then what you can do is find the mass of this object that's defined by two surfaces, even if the mass has a infinitely varying density. The density doesn't even have to be a constant. The density can be different at every point in this object, and we can still find a mass and the center of mass where this thing would balance. Okay? But that's Calc 3 stuff. That's Calc 3. Calc 2, unfortunately, is not as interesting as Calc 3. Calc 3 is very interesting. All right, so here's the deal. Right now, what I want you to be able to do is find areas under a curve by using this integration process. Like I said, next week, I'm going to do a proof of it, but right now, you're going to be asked to do things like this. Find the area under a sine wave.
What are the units?
Whatever units are used along the x-axis. If those are inches, this area would be in square inches.
So n was 1 inch, then you'd have 1/3 inch. area.
That's correct. That is correct. That is correct.
You can do this
You-
for velocity as well.
What's that?
You can use this as an average, if you have a velocity versus time graph, you can use it to find.
We're going to have a lot of applications in the next chapter. We'll find average value of a function, but we'll do that in this chapter, actually. Average value of a function. You could find the distance traveled, that kind of a thing. That's an integral, that's a summation. Any problem that can be solved by dividing it up into little teeny pieces and let the number of pieces go to infinity, as long as that can be written in a special way, called this Riemann Sum, we can solve it with an integral. Any problem that can be done. So if we have an area, okay, say this area, this y equals x squared area, and we whip it around the x-axis, we're going to generate a solid of revolution. Okay? Solid of revolution. Can you picture it? It's like, it goes up like this and it's rotated. It's like Mount Fuji on its side. Oh, it's a Hershey Kiss on its side. Okay? Hershey Kiss on its side. You got it? Okay. We can find the volume by doing what? Slicing it up in little pieces. Take a rectangle, whip it around, find the volume generated by that rectangle, get an infinite sum, and evaluate that infinite sum with an integral. Because that infinite sum will be the area under some curve. Okay? And we can evaluate it with an integral. Okay? And that's what we're going to do. And it's good stuff.
The units that you get, I realize, are sort of.
What's this? What were you hung up on units or what?
I read physics all day.
Oh,
That's
that's the problem right there.
Yeah, go and yell at them.
All right, well, go ahead.
So But it's in your unit squared, so if for whatever reason you were going to maybe move out of that unit into another one, you'd have to remember that it is in squared dimension, right?
Yeah.
It'd be like an inches squared.
We never get into that problem. That is a non-issue. I don't even write the units for these areas. We don't even need it, okay? But you're right. It would be in square units, whatever the units happen to be. And when we do those volume problems, solid revolution problems, those would be in cubic units, whatever those happen to be. Yeah. Okay, let's do a sine wave. Okay. Sine wave looks like this. Okay, sine. Let's do one arch of the sine wave. It starts at 0, goes to pi. Okay. We want to find this area, okay, under that curve. Well, I'll tell you, dividing it up into rectangles and letting the number of rectangles go to infinity is one nasty thing, because you end up with an infinite series in terms of sine, and we have no mechanism for doing it, okay? But we can do it with an integral. So let's do it. What's the area here in terms of the definite integral? It's equal to the integral from 0 to pi sine x okay. What's the integral of sine? Negative cosine. 0 to pi. What's the cosine of pi? Negative 1. Okay, so we're taking the opposite of that. So that comes out to be 1, which is what she was doing. She already took the opposite of it. And then put in a 0, so it's minus minus is plus. Cosine of 0, what's the cosine of 0? 1. The exact area under that sine wave is 2. 2 square units, whatever they happen to be. Which is surprising, given that sine is that transcendental function, and most values of sine are infinite non-repeating decimals, but the area under that sine wave is exactly 2 squared units. That's kind of interesting, I think. Go ahead.
On the length of 1 radian, you get an area of 2 radians squared.
So if this is, would say that again?
You have an x length of
Pi radians. Pi radian, yeah.
And you get 2 pi radians?
No, we get an exact area of 2 square units. 2 square units. That's what that would be. In other words, a rectangle here. What would the height of this rectangle be? Right here. What would the height of that rectangle be that has the same area as the area under the sine wave? Pi, no. Who said that?
No, I was about to do math.
No, somebody said it.
About
2. What the heck? It sounded like it was over here. Okay. 2 over pi. Okay, thank you. That's exactly what it is. This would be, the height would be 2 over pi. Why? Because the length of pi times its height of 2 over pi would give us an area of 2. That 2 over pi, by the way, is called the average value of that function. Well, we can do that while we're here. What the heck? The average value of a function is equal to 1 over b minus a times the integral from a to b of the function. Okay. Let's just check that out. In general, here's a function. Okay. The area under this curve, the area from a to b, is the integral from a to b of the function. That's what we're doing right here. The average value is the height of that rectangle whose area is the same area as the area under the curve. The average value, okay, is this height. So if you take the average value times b minus a, okay, times b minus a, what do you get? You get the area from a to b, the area under the curve. Okay, here's the average value. Oh boy, okay, average value, that's average down there, okay? That's this height. Times b minus a, this width, is equal to the area under the curve. So how do you find the average value? It's 1 over b minus a, bring this on the other side, times the area, which is the integral. Okay. I mention that because with a sine wave, there's an application here to electronics, okay? If you take the average value of this sine wave, okay, what's the average value of a sine wave? Everybody all set with this? Sam, you all set? Okay. Average value of a sine, wait, Rohila, you all set? Oh, almost.
What happens if we take the full period of the sine equation?
If we go from 0 to 2 pi, that's interesting. What do you think would happen?
0.
Was that? What'd you get? Actually, it's better if you don't say anything. Just move your lips because I can read them better. Okay, go ahead. It would be 0, yes. Sorry. It would be 0.
I just wasn't
Well, let's do it. We should do it. We'll check it out. But first, let me just give you this. The average value of this sine wave, okay, let's take a look at it. Okay, everybody okay with this? Okay. Would be 1 over pi times the integral from 0 to pi of the sine. That's 1 over pi times the area from 0 to pi. We did that out, and that area come out to be 2. So it's 2 over pi. Now that 2 over pi, I need an approximation. It's 0.7-ish. What the heck is that? 2 over pi I just need. It's around points.
Oh, it's really...
What is it?
7.28.
0.73?
I'm sorry, I'm doing it backwards. Never mind.
0.63.
0.63. Okay, 0.63 and change. That's an important application to electronics. It's the effective voltage of an alternating current, the average value of that sine. Okay, it's called the effective voltage of an alternating current. That's what it is. Okay. All right. Let's do Jacob's question. Let's find the area sine over this interval. Okay. The area is equal to the integral from 0 to 2 pi of sine x the integral of sine x, opposite of cosine x, okay, 0 to 2 pi. That's equal to, what's the cosine of 2 pi? 1. So you get negative 1 minus minus plus cosine of 0. What's the cosine of 0? 1, thank you. And that's equal to 0. Yeah, so the integral does that. As a matter of fact, if you have a curve, a function that goes beneath the x-axis, the integral will give you the area as a negative number.
So the area of the curve underneath cosine between 0 and pi would be 0.
Between 0 and pi would be 0 as well. Yeah, because you got the top branch and then you got the bottom branch. That's true. And if you had the integral, the area under x cubed, from say negative 1 to 1, what would that area be?
Twice the area of...
No, actually not. Here, x cubed.
Oh, cubed. I thought you said squared.
Oh,
My bad.
it's okay.
0.
Yes, if you had this, and from say negative 1 to 1, that also would be 0. Okay, here's what I want you guys to do. Find the area under y equals e to the x. Why don't you find the area from 0 to 10? Geez, I could actually do the proof today, huh? Could do the proof. What's that?
Can you read that? I can't see.
That's 10, what's that, this here part?
Yeah.
10 e to the 10th.
Thank you.
Yeah, I gotta be careful of that. Yeah, that's tough to read even. I've got to tell you, I'm going to do the proof today. What the heck? Might as well do the proof today. You know? What do you think? What do you think? Is that a good idea or not?
Don't do it, guys.
Don't do it.
Don't do it, man.
You stick to the plan.
The plan was not, but it seems to me you guys are with me and all, right? It's not like I'm losing or anything, right? Oh, wait, he's leaving. Oh, so maybe. I know. All right.
Derivative of EX.
I know. I'm not going to do it then.
And derivative of EX is EX, right?
Yeah.
So you're gonna have this one times this for the proof.
Huh? What am I going to have? This one?
You're gonna do the proof there.
I'm not going to do the proof. If you're going to leave it, I'm not going to do it. I'll do it on Thursday. When will this lecture be on YouTube? I don't know because it depends on Devin. I'm not sure when I'll see Devin again. Probably Thursday before class. I'll give it to him. So probably won't get up there until this weekend. But I'll tell you what, though. I mean, I have it being recorded. I'll have it on that SD card. I can take it back to my computer. I can put it on a flash drive or something for you tomorrow, say. Are you around tomorrow?
Yeah.
You come in and see me tomorrow. If you could bring in a little flash drive, that'd be even better. I'm here from 7:15, okay, which is tomorrow, Tuesday, until like 1:30ish, okay? Somewhere in there between classes would be great. You come in and see me, I can give it to you.
So what is the function on this? Is it x cubed or what's the?
No, e to the x.
Is e to the x is from 10 to e to the 10th?
It's from 0 to 10. And this point right here on the curve is 10 e to the 10th.
Okay.
Okay? That's what I'm asking you for. So, you're in the paper again. Every time I look at the paper, there you are. What, indoor tracker? Indoor something? Yeah. It's interesting. Okay. How we doing? Carlos, how you doing? You doing okay? Oh, okay. This point right here is 10 e to the 10th. I'm sorry. See, over there.
Did you ask if anyone got an answer yet?
I didn't ask that yet. Does anybody have an answer? Good. Who wants more time? Okay. What's the answer?
22,000.
Wow. What is it? Would you get 22,000?
Yeah, 025.
20,025.47.
Wow. Okay. Let's do it. I got to tell you, if this is on the test, that's not the answer I'm going to be looking for. Okay? I won't be asking for a decimal answer. I'll ask for the answer in terms of e. Okay? Just so you know. So, what's the area under this curve? The area is equal to the integral from 0 to 10, e to the x, dx. What's the integral of e to the x? E to the x. Substitute in 10. Substitute in 0, that's your answer. That's the answer that you'd see on the test, okay? E to the 10th minus 1, okay? Okay. Well, okay. So, how are we doing? You guys doing all right? I hate to go on and do anything else without Edwin here, but here, one more thing. Why don't you do this? Figure this out. We'll do one more thing. Let's take square root of x and x squared, and let's find this area. Go ahead, why don't you guys do it, and then we'll do it together. What's that?
Would you mind giving us the intersection point, or do you want to find the intersection point?
Yeah, you can find the intersection point. You guys can do that. See what you can do. We'll do this one last problem. And then I'll do the proof on Thursday, and we'll do some more. All right, well, we're in good shape. Your homework will be 5.2 and 5.3. Okay, 5.2 and 5.3. 5.2 is just on using sigma notation, is using those sums. And 5.3 is on using this limit process to find the area. But also using definite integrals to find the area. Oh, you don't? Oh. I did? Oh, man.
So would you just set it x squared equal to the square root of x to find your intersection?
Sure, absolutely. You hear it? Yeah, fine. All right. Who else? Who else has an answer? Mohit? And? Carissa, you have it? Oh, it's not Carissa. Oh, it's not Carissa? Are you sure? Where's Carissa? Oh, there's Carissa. Oh, rats! Karen. Oh, you're down here. Carissa's up there. You're down. Oh, fine. I'm sorry. Karen, you have it?
1/3.
Did I ask for the answer, Karen, or what? Oh, no, that's okay. All right. Yes, that is the answer of 1/3. Let's do it. Let's do the problem. Okay? Is that? No? Somebody else?
Where do you get the point?
Somebody want to disagree? What's that?
Can I disagree with that point? It's annoying me. It's the end of the day.
I can see that. You're being yeah. Let's find out what that point of Let's do it. I'm sorry to laugh at your annoyance, but.
I agree, I hadn't done the subtraction yet.
Okay, well, let's find the point first. Obviously, 0, 0 is a point of intersection. That's where it starts. What do? Set these two equal to each other. Well, what do you want to do? You got a square root thing there. Let's square both sides. Get rid of the square root. Okay? And now what do? In general, to solve an equation like this, set it equal to 0. Factor it.
X equal to 1, x equal to 0.
Yes. Set each factor equal to 0. So x is 0, that's this point. Or x cubed is equal to 1, so x is equal to 1. Those are the 2 points of intersection, 0 and 1. Okay? So, blush. So the area under the bounded by the 2 is going to equal, in general, when you have two functions and you want the area bounded by the 2, in general, you'll take the integral from a to b, where a and b are the points of intersection, and you'll take the top function minus the bottom function. Okay? That's how you find the area bounded by the two functions. It's top minus bottom. After all, if you take the area underneath this curve, okay, it comes down to here. You take the area underneath the bottom curve, and if you were to subtract the first area minus the second area, what do you get? The area bounded by the 2. Okay? And that's what we're going to do. This is the area bounded by the 2, so you get the integral from 0 to 1. Top function, square root of x. The bottom function is x squared. And integrate it. Add 1. We have an x to the n form here, so it's 3 halves. Divide by 3 halves times 2/3. Okay, x to the n form that we had from last time. X squared is x cubed over 3 from 0 to 1. Substitute in 1, we'll get 2/3 minus 1/3. Substitute in 0 to get 0. Okay, you get zeros in both. So you get 2/3 minus 1/3, which is 1/3. Okay. The exact area bounded here is 1/3, which, interestingly, is exactly what this area is. Kind of cool. That this line, this curve, cuts in half the area underneath the square root of x. There's 1/3 up there, and there's 1/3 down here. It's kind of interesting, I think. All right, but anyhow, that's what it is.
What is the coordinate of that intersection up there? Is that 1, 0, or what?
The point of intersection is 1, 1.
Up there, yeah. That's 1, 1?
Yes. When x is 1, the x squared is 1, and the square root of x is 1. That's the point, 1, 1. Go ahead.
There's no integration constant?
No, that's interesting. When you have a definite integral, what we'll see next week is we'll solve for the constant. And when you do this integral,
You get like a series of
well, you get some antiderivative from a to b, which is capital F of b minus capital F of a. This here is our constant of integration. We'll solve for it on Thursday. We'll solve, so you don't have a constant of integration when you have a definite integral, because it's right here. Yes. Yes. All right, how are we doing? All right, so here's what you should be doing. For Thursday, you should be doing 5, 1, 2, and 3. I think all of 3 is in there. And what we'll do is we'll do the proof showing the connection between the area and the integral. And what we'll have then is this. We'll have an area under a curve is equal to an infinite sum. We'll have an area under a curve is equal to the integral. Okay? Therefore, that infinite sum is equal to the integral. Okay? And that's going to be critical to doing our applications. Okay? As long as we get that infinite sum, we can evaluate it with an integral. Okay? And that's what we're going to do for our applications in the next step. Okay? Is everybody okay? See you.
Yeah, Mr.
Wait,
Harris.
see you. Now, somebody, I was going to give the video to from last class for you. Jason. Jacob. You want the video from last class or not? No.
Can I see the notes just so I can take down the...
You want the notes?
They know the first one for the homework. They know the title for the homework, first page.
First page?
Yeah.
Here, let me get these in order. Holy man, look at all the stuff I did today. Working like a dog. Okay, first page. What about it? You want it?
Yeah.
You want to look at it? You want to?
No, that's the first page.
You want to take it?
Yeah, I want to take a look.
Oh, take a look at it. Here, take a look at it.
That's the only answer. You know, forget how your bones feel.
Hey,
Hey, what's up?
You know how we had that conversation on Thursday about Wednesdays?
Oh, yeah.
I can't because Wednesday I have a meditation class. It's
A
meditation.
Zen class?
I had meditation.
Meditation,
I
not
had
Zen.
I had to take. I had to take it because I wasn't full time. So
Give it next one.
Okay, you'll give it to me next week?
No, Thursday.
Thursday, good. Yes.
It's also sun and moon.
so this is how my schedule looks like.
What the heck? It's all messed up. Carolina, what the hell is this?
That's my schedule.
What are you doing here? This period, you're going crazy? Is that what that
Oh
means?
no, that means I'm.
Go crazy. You're off totally on Friday?
Yes.
All right, here, hold on. So, let's see ya. You okay? You still all annoyed or what?
No, my first class was at 9 a.m.
Guess what my first one was at?
7:15.
No, well, 8 o'clock.
8:30.
8 o'clock.
Good enough for me.
Oh, for you? All right. So, yeah, that's a long day. That's too long. I agree.
It was the one bit that was annoying me, and I was like, I'm almost sure this is 1.
Yes,
And
that's
don't.
it.
Yeah.
She's welcome to my class anytime.
Yeah, apparently her dad's not getting her at 7, so I guess she'll be here the whole
Oh,
time.
yeah, that's right. We missed her.
Yeah.
Okay, well, she's welcome anytime.
All right.
Even if you're not here, she can come to my class. All right?
All right.
See ya.
Have a good night.
You too. So, oh, Carolina, we gotta think of something else now. I thought we had a cool solution.
I know.
All right.
I mean, I can print you like a regular copy if you want. I'm not.
No, I don't
I'm
care
serious.
about that. I believe
I'm
you.
not.
No, jeez.
I literally forgot because it's like
I
once a
believe
week,
you.
and I'm like,
Oh, jeez. Guess what?